Thank you for coming. And thank you, Scott, for the introduction. I see you went with the short version. That was a joke. That was embarrassingly long. As Scott mentioned, I'm a practicing geotechnical engineer, and I spend most of my time these days with various tailings design and construction projects. And what I'm going to share with the group tonight is a couple of presentations, one of which I gave in Oslo last fall at the Tailings workshop that was hosted there. And the second one, which I'm going to give later, was one that I presented at GeoCongress in Vancouver earlier this year. And they complement each other. The first presentation deals with some field investigation and interpretation for assessing the liquefaction potential of some problematic silts and sands that are quite prevalent within Canada, across the Canadian Shield, where glaciers have kind of left behind ice treats for us to deal with in the form of Glaciolacustrine deposits. And the second is actually more laboratory focused, and will address a very specific issue that I'm going to introduce in the first talk. So again, the specifics of the first is looking at the state parameter estimation of micro-laminated glaciolacustrine deposits. And I'm not going to disclose the exact site this comes from, other than to say it's from a mine site in Northern Ontario. And before I start, I want to first start by acknowledging that actually, although this is a tailings working group and this is a tailings project, the material that we're dealing here isn't tailings. And I want to start with a bit of a focusing statement, in that we tend, lately especially, in the last 5, 6, 7 years, since some pretty catastrophic failures, in one in Canada, one not far from here, much less catastrophic, but a failure nonetheless, and 2 in Brazil that killed a lot of people. The focus has been around this liquefaction potential of tailings. But one thing that I really wanted to point out is that many of our failures in dams that have happened historically, including 3 of the 4, if not all 4 of the ones I just mentioned, actually were fundamentally problems in the foundation. Foundation failures in the soils and weak rocks in the foundation that then triggered what then became subsequent liquefaction and flow failures within the contracted tailings above. And so the example that I'm going to talk about here is actually one of the potential for assessing, this brittle response in a foundation soil upon which a tailings dam was being built, and really understanding, what the potential was for that material to liquefy. And so just a very quick geological history lesson, which may be familiar to some in the room and may not be to others that haven't worked in North America. The depositional history of the material that I'm going to discuss is a material that was deposited in glacial lakes following the glaciation of Canada about 10,000 years ago. Here's a look at the maximum extent of the Laurentide ice sheet that covered Canada and half of the United States, and those contours are 1,000 years before present, so you can see at the maximum extent, and then as it retreated towards the north, meaning 18,000 years ago it was at its maximum extent, and then you can see as it retreats towards Hudson Bay, which is kind of an outline in pale white, about 6,000 or 7,000 years ago. And here again, this is a look at the extents of that ice as it was retreating and melting. And what ended up happening essentially is it formed a massive super-glacial lake across most of central Canada, which is referred to as Lake Agassiz. And it's in that lake that that silts, sands, and clays were deposited, depending on the year and the extent. And one thing to remember is that it was a very dynamic process, and that ice sheet was, as it generally was retreating, it was periods of cold when it again then advanced and then retreated and advanced and retreated. And what we were left with was a lake environment where silts and sands and clays were deposited, with clays being further away from the ice sheet in a more quiescent environment, and silts and sands being deposited closer to the ice front. And again, because of the dynamic nature of the advance and retreat of that ice, what ends up happening is we can end up with sequences of silts, sands, and clays which are laid down in a laminated structure. Not unlike what we actually often see in a tailings facility, again, depending on discharge location, with sands typically being closer to the point of discharge and slimes or clays being farther away. And so one of the things that this does is it creates materials that can become tricky to interpret because of the constantly changing nature. And with, as most people in the room know, when we're trying to characterize liquefaction potential, we're often dealing with sampling of materials that we then have to reconstitute into laboratory specimens and test, and then use the results of those tests for interpretation. And so the focus of this talk are some of the key challenges with dealing with those soils and the implications when it comes to liquefaction assessment in these laminated deposits. So, the intent here is not to teach critical state mechanics in one slide, and I do apologize for those that aren't necessarily practicing in this world, because this is maybe a little bit technical for general talk. But I did want to, at the very least, explain the state of practice for liquefaction assessments and the methodology that was followed in this work that I'm presenting, with some high-level explanation or understanding, starting with the general process we follow. The first step being a field investigation where we drill boreholes and we push CPTs or cone penetration tests to characterize the in situ behavior and characteristics of the soil. The second involves laboratory testing. Our friends from Triaxial know all about this, because I think a lot of the work they're doing, for example, involves critical state testing of laboratory samples. And what we're doing when we do those tests is we're determining what we call the critical state line, which is a material-dependent relationship when plotted in density versus stress, or void ratio versus stress space. It forms a line, and really what happens is, if you're a state of soil above this line, you're in a contracted state, which means when you shear, the volume is trying to get smaller. And these are the materials where, in an undrained situation, pore pressures are going to develop in that case, because it can't contract, it puts pressure in the soil, and in extreme cases, you end up with materials that liquefy. If you're below this line, it means you're in a state where the sample is dense relative to the critical state. If you shear that sample, it's going to dilate, and again, if it's undrained, that's going to actually cause negative pore pressures. It's going to try to suck water in, and that results in increases in effective stress and a corresponding increase in strength. And so, to put it very generally, if we can show that our sample or our in situ material or tailings in the tailings facility, whatever it is, if we show that the current in situ state is above the line, that's what's shown here with this negative emoji, That's a bad news situation, because that means we're susceptible to liquefaction and brittle failure, and this is the cause of some of the flow failures that we're all familiar with. Whereas if we can demonstrate that our in situ state is dense of the critical state, our materials dilate, it's going to behave in a ductile manner, it's actually going to get stronger in undrained shearing, and everything is good. Now, so then the trick becomes, well, how do we determine where we are relative to the critical state? As I mentioned, we do laboratory testing to evaluate the position of the critical state, and that's done through a combination of drained and undrained triaxial tests by, for example, preparing a sample to a known void ratio and then shearing it drained and allowing it to contract, and shearing it undrained and letting the pore pressures develop. And again, the end point of these stress paths corresponding to the critical state, which is the point where shearing doesn't produce any ongoing volume change. But then the question, as I said, becomes, well, how do we get the in situ state? And sampling of silts and sands is very difficult, because in just pushing our samplers, it creates disturbance that, we quite often will end up with a sample in a density or state that's not representative of our in situ conditions. And so a lot of focus in the past decade or more has been around interpretation of in situ tests, in particular the cone penetration test, and correlations then to tip resistance that we can then use to infer the in situ state, the in situ void ratio. And the state of art or state of practice with that is, it all stems really from work that Mike Jeffries and Ken Bean developed, and Don Shuttle has introduced, using essentially what amounts to simulations of a cone being pushed into the ground, and using cavity expansion theory, which is the, how the response of the cone as it gets pushed can be modeled in finite element. And it relies on a whole bunch of literature tests, chamber tests that have been done where somebody has prepared various different sands in a laboratory environment and then pushed a cone through them to develop correlations. And so this is an example from a recent publication by Mason Gafkazi and his team at the University of Toronto, but it just shows you some examples depending on the soil parameters as determined from critical state testing. We're able to develop these relationships between cone resistance and the in situ state parameter, the in situ density, that we're then able, from that, what we're able then to do is to use our cone penetration tests and are able to convert the tip resistance directly into what we refer to as the state parameter. And the state parameter is essentially the distance in E void ratio space between the point where we're residing and the equivalent void ratio at the critical state at that stress. And really what it means is if that value is positive, it indicates that we're above the critical state line, we've got a contracted material, it has the potential to liquefy. If we're below the critical state, it means we're in a dense state, it's going to dilate, and again, a negative state parameter indicates dilation, we don't need to worry about liquefaction. And so again, we use this theory, we use our laboratory tests, we convert tip resistance, and we identify areas where we have contracted soils with state parameters above 0. And again, for example, from this case, you can see this region, for example, as being susceptible to liquefaction, another one down here. And so, like I said, this is the process, the state of practice for dealing with in situ silts and sands. Now the challenge, and what I'm going to get into in this presentation is, how does this process work when we're dealing with materials that have laminated fabric that are, it's not as simple as just saying, well, one set of properties or one set of parameters applies to all of that material, because there is, it's changing. In other words, you've got millimeter scale silt, and then it's sand, and then silt, and perhaps some clay, and it's not as simple, and it's not as easy or not as simple just to apply one soil parameter to that material. And so what this gets at is, you know, how do we handle those materials that have laminated fabric using this framework, which effectively, as I said, is really geared towards uniform or homogeneous soil deposits. So, as I mentioned, the first step, site investigation. What you can see on the left is some simplified stick logs of the geology. And this is very, very common geology for the Canadian Shield in these glacial lake deposits. What we have in this case is a peat deposit above. We've got a Glaciolacustrine package, which, as I described before, varies between silts and clays and sands depending on the proximity to the ice at the time of deposition. And it's underlain by tills, either glacier or lodgement tills, and then finally bedrock. And so this project site, the material we're particularly interested in is this sequence of, again, silts and sands, which were, you know, loose enough for to be causing concern from a liquefaction standpoint. And when I talk about laminations, I guess I want to just show an example of, or different examples of what we often encounter. The far left being a varved clay with essentially lamina being of a noticeable thickness that's measurable, where you can see the pale zone essentially reflecting the silt and sand component, and the darker brown being clay. What we have in this photo, moving to the right, is micro-laminations, where it all kind of looks the same, but at the same time you can clearly see silt and sand partings, which are identifying these lamina of gradational change within the sample. Here's an example where it is laminated, but you can almost barely tell it's moving towards a homogeneous deposit, and then finally a homogeneous clay on the right. And the material that I'm going to be talking about is actually reflected more by this photo. Varved materials are easier to manage typically because we can actually isolate the individual varves and treat them actually as separate or discrete layers within the deposit. But it's these guys where there just is no effective way of isolating the individual lamina that present the most challenge. And again, not unlike in a tailings facility. So what I'm showing here is applicable to many tailings deposits where we see this, you know, change from silt to sand to clay-sized particles within the profile. So on this slide, I'm showing the family of gradation curves from the broader site investigation. So you can see it's obviously quite variable. The two materials that we tested, the blue and the green, referred to as GLU1, being slightly coarser, and GLU2 being somewhere in the middle of that cluster. And again, I point out that these are kind of average grain size curves representing the material as opposed to being a true reflection of the individual lamina. And I mentioned before, the first or the second step once we've done our investigations and collected our samples is a series of laboratory tests, in this case triaxial tests, where we take the material, we blend it, we mix it all together, and then we start preparing samples to known void ratios, and then shearing them in this case undrained, and these two drained. These are loose samples that are trying, or these two are contracting, these are trying to contract. And again, the end point where those samples go to, by definition, is the critical state. And with those tests, we're then able to determine the critical state line, which is, again, the first step towards our liquefaction assessment. And we also do dense tests, and you'll notice that these guys, really what ends up happening is they're moving along here and then starting to try to dilate, and they tend to be turning up and trying to reach the critical state. And then unfortunately, quite often with dense tests, they don't actually reach the critical state, and the reason for that is actually the subject of the second presentation. It's to do with sample non-uniformity and shear bending, which occurs in dense triaxial tests. So I want you just to hold that thought for a minute, at least until we get to the second presentation. But nonetheless, we do these tests because we learn quite a lot from them at the onset of shearing, and we use that data to develop constitutive models, in particular the Norsand constitutive model for silt and sand, which rely on not just the critical state line, but also what we call stress dilatancy and state dilatancy parameters, which we get from the dense triaxial tests. So that was for GLU1. This is a look at GLU2. Again, slightly higher in elevation, but similar in terms of the overall slope, a little bit steeper, which indicates a bit more compressibility, because this material is a little bit finer. And looking at them together, what we see is, okay, for these two soils, we have these two critical state lines. And again, this is fairly routine. We do this on a number of projects. But what we then did on this one, and again, I guess before I get to that, these just show, I mentioned the Norsand model. There's the process that we go through in calibrating or developing a constitutive model that we're then able to use to actually effectively simulate and calibrate to the various triaxial tests. And it becomes very powerful for a couple reasons. One, because once we've developed that model, we're able to predict behavior at any combination of state or density and stress for both drained and undrained conditions. And but it's also then used when I mentioned that process for estimating the in situ density or in situ state parameter, that relies on the Norsand constitutive model. And so we develop it for those reasons. And you can see some of the fits, both for, in this case, drained tests, in this case, undrained tests. And again, that point that I was mentioning before, where it starts to dilate and then it kind of stops, that's, again, attributed to shear banding and non-uniform sample deformation, which I'm going to get to in the second presentation. And so, what we did on this project, and this is where things got kind of interesting, was we had done a bunch of testing previously on the project on in situ intact push samples. And when we had developed these critical state lines, I asked the question, well, what if we plot our results from previous testing that we had done on intact or in situ samples and see how they compare? Because in theory, if it's the same material and we use the hypothesis that the critical state line is unique for a given material, then really those should all have been converging on those critical state lines. And what we actually noticed is, first of all, the in situ void ratios were above either GLU1 and GLU2, which was an indication of, wow, this stuff is really loose and liquefiable. But if we look at the stress paths, what we noticed when we sheared them undrained, rather than diving off to the left, which would be an indication of massive strength loss, these samples dilated and they moved to the right towards a completely different critical state line than the ones that we had just spent all this effort determining for those materials. And so this definitely caused us to stop and then try and figure out what was going on, because this is, we didn't understand it, and we have to understand. And so we didn't have any more GLU1 or GLU2, so we ended up doing some experiments on the closest material that we had, which we call GLU3, and that's what's identified here by a black line, which is found gradationally somewhere in between GLU1 and GLU2, at least in terms of the average gradation. And we started by, well, let's establish the critical state line for that material with the same process we had used for 1 and 2. So we took the material, we mixed it, we blended it all together, and we did 2 tests, 1 drained, 1 undrained. And what we found was, well, there's another critical state line for this material. Gradationally, it was very similar to the other 2, but it's going to, we learned 2 things. One is that it's going to a CSL that is higher in altitude or position, but the other was that the slope of that critical state line was very similar to GLU1 and GLU2. In fact, it was identical to GLU1. And now that didn't necessarily surprise us, because the slope of the critical state line is very often consistent if you're dealing with the same material from the same mineralogy, the same origin, the same depositional history. But the gradation can be quite varied. If the gradation varies, the position of that critical state line can kind of move, because that has to do with the packing ratio and how the voids are filled with finer sediments. But it did interest or surprise me anyway that it was way up here when it was actually very consistent to the gradation of 1 and 2. And so we started by, okay, well, maybe this is the answer. What we're clearly seeing is that minor variations in gradation are greatly affecting the position of the critical state line. So, and that, if you'll remember or recall from the previous slide, the cluster of in situ tests was up here, and so this led us to think that this was just explainable on the basis of those samples were obviously slightly different in gradation and therefore different in position. But then we took a sample of the same material, GLU3. This time, we didn't mix it up, we tested it intact. And what we found, it happened to start at a state that was very handy to the critical state line, which should have indicated, when we ran the test, it should have neither dilated or contract. But lo and behold, the material dilated all the way up here, again, appearing to be moving towards a different critical state line. And so this caused us to revisit again what is going on, because we thought we had it figured out, and now again we're seeing totally different behavior for the same material. And the last step for this kind of process was, once this test was finished, we physically took the identical sample and we mixed it together and we reconstituted it back to the same target initial void ratio to try and see if the behavior would change for the identical material depending on sample preparation, the difference between intact and reconstituted. And what we now saw is, by remixing it, now it contracts and it's moving back towards the interpreted critical state line for that material. So this was direct evidence that for the same material, it's moving towards a different critical state line when it's intact versus when those lamina are broken apart, it's mixed together, it's reconstituted into a homogeneous sample, and the test is repeated. Which, I'm sure, for anybody that's in this world is a huge problem, because what this now implies is the critical state line is actually not unique, and we can't use any of this theory for predicting the behavior. It's a fundamental assumption when we're doing this critical state, these liquefaction tests, that the CSL is unique and it's not fabric dependent. And so at this time we thought, oh great, well we've just wasted this entire effort on characterizing these materials and now we can't do anything with them. But there was a little bit of a silver lining here, which was we made the assumption or interpretation here that although these are moving to different critical state lines, the slope of the critical state line is consistent for these different materials, again, owing to the fact that they're from the same geological origin. And so we said, okay, clearly this test is moving to a new CSL that's out here, but what if that critical state line is parallel to this one? And so we interpreted what we're referring to here as an interpreted intact critical state line. And the reason that we did this is to see what effect the position has. If we can say that the slope is the same, what effect does the position or the altitude have on if we were to carry forward with our standard interpretation methods? And what we learned very quickly was only changing the position of the CSL without changing any of the other parameters, including the slope, which is the main thing, we are able, without doing anything to our constitutive model, it very reliably is able to capture the behavior of the material. And so what you can see here is a calibration or comparison between our constitutive model and our test data, which again is able to really reliably capture that behavior. And so that's really important because if the slope is the same, what it's telling us is that the interpretive methods we're using and the North-Sand parameters and the constitutive model we're developing is reliable as long as we know that slope is parallel. And why that matters is because the interpretive methods that are used, the cavity expansion process, the process that Mike Jeffries and co-developed, is not sensitive to the altitude or the position of the critical state line. It's only sensitive to the slope. Because the cone, as it's pushing, and this is the power of the state parameter as being the metric, it's really just looking at what the pore pressures are doing. Is it dilating or is it trying to contract? And it's really, when you go through the whole cavity expansion process, what it's really doing is just telling you where you are relative to the critical state line. It's not telling you where the critical state line is, it's telling you where you are relative to it. Meaning, if it's developing negative pore pressures, you're dense. If it's developing positive pore pressures, you're loose. And so what it actually means is, again, back to as long as the critical state line is known, and as long as you can say that it's parallel, then the interpretive methods work. And so there's actually a validation or a check that we did. Here what we're showing, again, this is an example borehole or a CPT hole where I wanted to use this one because this is one where we actually have that in situ sample that we took. And what you can see is the state parameter according to the cone is hovering around between about 0 and minus 0.1, depending on depth. And yeah, so, and again, they're overlaid on top of each other here, but what this is demonstrating is that the gamma term, meaning the position or altitude of the CSL, you get the identical cone trace, state parameter trace, regardless of what, because again, that doesn't enter into it. Now, What we don't know is perhaps some of the other constitutive model parameters are also changing, and perhaps those could impact the results. So we did some sensitivity analyses where we varied the state dilatancy and stress dilatancy parameters, as well as the hardening coefficients. And what we actually showed is that although it changes very, very slightly, these interpretive methods are not actually sensitive to changes in the other NORSAM parameters. And again, this was encouraging because it meant, well, even if those do vary on the basis of the fabric, it doesn't change the overall outcome. Now, what did change it, again, was changes to the slope of the critical state line. So we did some sensitivities where we varied the slope, and you can see that it actually has quite a significant impact now on the interpreted state. But again, we have good evidence from our testing that that slope is actually not changing. And as a last check, what we then said was, well, if what we're saying is true, then that initial test, CIU 311 for example, if its intact critical state line is up here, and if the critical state line is parallel, then we should know what the actual in situ state parameter was of that sample directly from the laboratory data, and it corresponds to a state of minus 0.04. And so if we're right, we should be able to go to that cone trace, go to the depth that that sample was taken from, and check that the interpreted state parameter matches what we got from our intact laboratory sample. And that's what's shown on the far right, where we plot a dot at minus 0.04 at the sample depth, and it matched perfectly. So this is another validation that, first of all, our assumption of a parallel critical state line is accurate, and that we can use these methods even in laminated deposits where we have this fabric that's almost impossible to quantify. Just by virtue of the way this particular method works, we're able to use it to reliably estimate the in situ state and the liquefaction potential of the material. So, in conclusion, the critical state line varies in altitude within a micro-laminated glaciolacustrine deposits, and in fact, there's very likely to be an infinite number of critical state lines depending on subtle changes in the gradation. But they're very likely going to be parallel as long as the source material, the mineralogy, is constant and consistent. The altitude of the position of the critical state line may not be unique, and this is a big finding because, as I said, this assumption of a unique critical state line is fundamental in these methods. And what we've shown is, in fact, the critical state line may not be unique, but as long as the mineralogy is constant, the slope of the critical state line is unique, and that is the fundamental most important thing when we're using these interpretive methods. And so provided the slope remains unchanged, the fabric effect here associated with lamina does not appear to adversely influence the results of using these in situ interpretations for characterization of the in situ density and thus the liquefaction potential of laminated deposits. And as I said, this is a laminated soil, but it's totally applicable to tailings, for example, which also suffer. And in fact, this is a huge point of debate in many conferences with many researchers that are saying these methods don't work for real world problems because in the real world, these soils have fabric. They're quite often laminated. You cannot just take these parameters for reconstituted materials and apply it. And what this demonstrates is that actually you can, as long as you can develop confidence in the fact that the shape of the critical state line is consistent amongst the different materials. So I think that's the end of presentation one. I have another one that I'll get to. I don't know the best way of handling questions and answers, but I'm very happy if people have questions to answer them now before we move on to the next presentation, if that's the best way of doing it. Yes, so does anybody have any? Yes?
That's really interesting. You interpret it in a different way.
Yeah.
But in terms of the new calibration by increasing the altitude for the new slope,
Yeah.
which technically you increase in the void ratio.
Yes.
Another interpretation is you have it fresh tailings because they are not really sedimented and deposited, because of void. So is that indirectly saying your method is suitable for the fresh tailings?
Do you mean as opposed to cemented?
Yeah.
Like if there's a cementation
In terms of the void
effect?
ratio, because
So the thing is, the way you have to think about it is that yes, the void ratio may go up, and that's where the struggle is, because if it goes up and now it moves above the critical state line, then you're in a contracted state and you have to worry about liquefaction. The thing though that you have to remember is that's true if you're dealing with absolute void ratio, but if you're dealing with state parameter, then as the void ratio goes up, the critical state line actually goes up with it. And so you're not changing the relative position of the in situ state relative to the critical state line. And that's the fundamental power of dealing with state parameter, which is what you get from these interpretive methods of cone penetration, for example, versus dealing with just absolute void ratio. So there is a caution here, which is that if you've developed a critical state line, for example, from a reconstituted test, and then you use a different method for assessing the in situ void ratio. So for example, you just were to get an undisturbed sample, if that's ever possible, in silt and sand, and you were to measure its density and know its specific gravity, and you get the in situ state for that sample, or in situ void ratio. If you then plot that on the same plot, it's going to show up as being highly contracted and very misleading, because it's comparing an absolute void ratio to a critical state line that's not applicable to that. And that's what we saw when we plotted all of our past historic tests onto that plot. But as long as we're dealing with state parameter as opposed to natural void ratio, then the relative position moves together, and that's what's happening here. And that's why we're getting the correct answer, even though the critical state line is not unique in that case. Any other questions? Yes?
Can you work through how you move that state line up again on that slope?
Yep. Oh, sorry.
I jumped in. Because I think that's the critical thing. Just walk through the logic again, because I sort of lost you.
Okay. Yeah, go back. Go back. Go back. Here. So what we did, it's quite simple actually. This test, which was the intact specimen, when we sheared it, undrained, it dilated. But at the end of the test, it had reached the critical state. It had reached equilibrium. The pore pressure was no longer trying to change. And so what we can say fundamentally is for that intact sample, we know at the end point it was at the critical state. So we know the critical state line goes through that point. And so that's a fact. Now the assumption that we made was, well, if the critical state line goes through that point, and if it's parallel to this one, because it's the same material, then it has to have that shape. And so that's how we developed the critical state for the interpreted material. Pardon?
Just on the 1 point.
Just on the 1 point. But we were able to validate it by in two ways, because again, it's an assumption. But what we then we were able to validate it because we take that one test now, and we don't change any of the north sand properties, and we don't change the slope, we don't change anything. The only thing we change is the position of the critical state line. And what we found right away is that we ended up with extremely good predictive matches from north sand to the parameter. The second validation, again, which I showed at the end, was that with the assumption of a parallel CSL that passes through the point, we can then determine what the state parameter was for that sample, and it matches perfectly, in this case, without fudging, and I promise there was no fudging. It matches perfectly with what we get from our in situ trace.
That was the purpose of the underground.
Correct. Exactly.
Second line through.
Yeah, exactly. Yeah, any other questions on that? Yeah.
I'm from 1960. I just would like to ask you, it seems to be you test the sample on the dense side of the critical state line. Is it the final void ratio? Is it correct? Because normally, if you test the sample on the dense side,
yeah,
you get the searback.
Well, thank you for that question, because that's the subject of my second presentation. This particular sample did not shear bend, and so we were able to confirm that it reached the critical state on the basis of first of all, the relatively uniform sample deformation, as well as the trends in terms of pore pressure. So yes, it didn't shear bend, but that is another very important point, that quite often with certainly dense drain tests, we end up with big shear banding problems. Less so often with undrained tests, but at either rate, this one didn't, and so we were fortunate that we were able to use it for that purpose. What time is it? Okay. This second presentation doesn't go as long, so. And in fact, it'll be good that I went through some of the tedious details in the first one, because it'll help with presenting the second. So the specific focus on this talk is aimed at addressing one of the comments that was just made, which is, can we reliably use dense tests for this critical state purpose? And because part of the issue is, again, this non-uniform stress and deformation distribution, which really limits the usefulness of dense tests in triaxial. And so there's a little bit of a history lesson here, which will be interesting to perhaps very few in this room. I know my tri-lab friends will be interested. I'm not sure the rest of you, so bear with me. But triaxial tests on samples are very often, most often, carried out on specimens with a height to diameter ratio of 2 to 1. Conventional testing, for example, being on 70 millimeter diameter by 140 millimeter high samples. And the basis for that was in the 1940s, Skepton did some research and showed that if you have a sample that's twice height relative to the diameter, then the effects of end friction essentially go away. And he was focusing more on peak strength, but the conclusion was we don't have to worry about end effects when we have samples that are at least 2 to 1 height to diameter. The problem with that is we can end up with sample instability. It's almost effectively a buckling that occurs, which again is prevalent in dense samples, and I'll explain a little bit in a minute why that is. And so actually there was a lot of research done in the 1960s in the UK by Rowe at Manchester and others at Imperial, where they try to improve the Triaxial state of practice. And what they did was they introduced what are referred to as lubricated free ends and oversized end platens. The idea being, a lubricated free end is effectively a latex membrane with grease that's cut in a donut to allow drainage through the middle, but the rest of it is a very low friction end. And what they showed was that with the advent of lubricated ends and oversized end platens that would then prevent the membrane from restricting the lateral growth of the sample, they were able to shorten the sample to height to diameter of 1:1, which prevented or precluded this buckling shear banding effect without impacting the overall results. And so this was a great improvement for triaxial testing. And one of the great kind of mysteries is that these processes of using oversized end platens and lubricated free ends has now been widely adopted in industry, especially when we get into these very sophisticated liquefaction tests which require really accurate procedures to make sure that we're doing everything we can to understand things like void ratio and distribution of stresses. But for some reason, we still test samples at 2:1. And the use of 1:1 has never really been widely adopted in practice. It's still out there in academia. There are some researchers, Cedric Karimi being one at Western, that tests at 1:1. And there are others, but in terms of practice, the convention is still 2:1. And just as an example, in the round robin on critical state testing that some here may have been involved with, it was done in 21 by Dave Reed and his team at UWA. There were 18 laboratories that participated. All 18 of them tested samples with a height to diameter of 2:1. So the study that we did here was carried out to better understand what effects the height to diameter ratio has on triaxial testing, specifically carried out for CSL determination. And again, it's a bit of a revisit of some of that work that was done in the 40s and 60s. Again, but rather than be focused on peak strength, it was more, this study was focused on the critical state and the interpretation of those critical state lines, and are they influenced by this difference? And so, an overview of the program, we did tests using GDS Triaxial equipment, which is very standard for this type of testing. The oversized end platens with 85 mil for a 70 mil diameter specimen. I mentioned lubricated free ends. Here's a look at the different molds that we used to create the samples, both at 1:1 and 2:1. This is a schematic of the lubricated free ends, which again is a latex membrane sandwich with grease, with an inside small diameter porous stone. We prepared the samples by moist tamping, saturated them until a p-value of 0.98 or higher, and we did 30 tests with a pretty even split between CIU and CID. The sand that we tested, and again, what we're doing here is certainly very applicable to tailings, but we didn't actually use tailings for this testing. We used a sand that we're calling Fredericton sand, which came from a local boro source outside of my hometown in Fredericton. The reason for that is because we have an infinite supply of this material, and we're able to use it. We've got a number of different ongoing research programs where we're using the same material. And so that's why we chose a sand. This sand is a quartz feldspar sand, and that's relevant because because of the feldspar contribution, it actually has a higher strength than maybe a lot are typically used to seeing. but otherwise it's just a very standard glaciofluvial sand. Fairly angular, and again, just some of the parameters. Here's a look at the grain size curve. So, we started with the 2-to-1 tests. We did a number of drained and undrained, again, prepared to different different prepared states, and essentially did enough tests that we could very reliably determine the critical state line, which for this material actually has quite a curve to it, which I think is probably no surprise to many that are dealing with these materials. The curvature is a combination effect of compressibility of the particles, and in this case more to do with crushing actually of the particles and crushing of some of those angular edges, which gives us this curvature. But you'll see that in every case, the loose tests all converged on a unique critical state. And then we did the dense tests, and you'll see again, as we saw in the first presentation, that invariably those tests, and in some cases they did actually start to dilate and then continued on up, but they didn't reach the critical state line. And the reason that they don't reach the critical state line is if you picture a triaxial specimen that's prepared dense, and we start applying axial force, and it's starting at this void ratio, what happens is there's an infinite number of shear planes that are developing within the sample, all oriented at 45 plus 5/2 on the plane of maximum obliquity. But eventually, in a triaxial sample, especially one with a slenderness that's effectively skinny relative to its height, one of those planes punches through from one side to the other, and it then becomes the dominant shear plane. Now, on that shear plane, the material is reaching a critical state. On a dense test, it's dilating. But once it dilates along that shear band, it's now the loosest part of that sample. Everywhere else in the sample, it's denser. So the shearing doesn't want to go anywhere else. So as soon as that shear band forms, then what ends up happening is you just end up with two wedges sliding past each other, and all dilation stops in the sample. And where that happens, it kind of depends on the nature of the material. But what you can say for sure is that, within the shear band, you're at critical state. Elsewhere in the sample, you have no idea what the void ratio is because it was starting to dilate and then it stopped. We can tell at the end of the test what the average void ratio for that sample is, and that's what we're plotting in the red dots here. But we don't know. That doesn't really help us because it's not reflective of the true void ratio along that shear plane, which is indeterminate. And that's the big problem with these dense tests. Now, if we compare that to our 1-to-1 tests, which we did, we basically repeated all of these tests with 1-to-1 samples. And again, what you can see is that all the loose tests go to a unique critical state. But now, with our dense tests, what we see is that those are also all reaching the exact same critical state line. And again, the reason for that is, and again, ignore this cartoon because this should be showing a 1-to-1 sample, not a 2-to-1. But the idea being, those shear bands, when they start to form at a 1-to-1 sample, they get interrupted because they're at 45 plus 5/2, they're not able to daylight on either side of the sample. They end up running into either the top or bottom cap, and that then forces the shearing to start to occur somewhere else. And you end up with a much more uniform sample, where the entire sample is now at the critical state at the end of the test. And so now the question is, well, okay, so how do these compare? Well, when we plot them on top of each other, there is no significant or statistical difference in the critical state line. They're identical, whether it's 1-to-1 or 2-to-1, which is good because now what we've learned is that there is a drastic improvement in the behavior in terms of being able to get value out of the full test and using that to inform on the position of the critical state line and all those stress, state, and latency parameters without any undue influence on the determination of the critical state line. Now, one of the interesting things is, as we know, the critical state line is a 3D line which exists in E versus Q versus P space, and we're typically used to looking at it in a 2D projection. What we just looked at was the E-P plane. If we look at the same line in our Q versus P space to look at the frictional strength, we actually do see that there is a subtle difference. So with the 2-to-1 samples being slightly weaker, with an MTC in this case of 1.5 versus 1.6 for the 1-to-1 samples, and that corresponds to a change in, or a difference in friction angle of about 2 degrees. Now, when you throw it all together in the grand scheme of things, whether or not this is a true statistical difference or whether this is scatter, it's a bit hard. They're awfully close, but there is, you know, if you run regression, there is a difference. And again, the reason for this difference isn't totally clear. And I'll come back to that in a second. But we can also see, just in looking at some of the behavior differences, again, these are comparison plots of material that's been prepared to the exact same void ratio in drain versus undrained tests. This being, in this case, drain tests and comparisons between 1-to-1, 2-to-1. You can see in stress strain, again, that's the point where dilation stopped and a shear band took over, versus the 1-to-1 that continued to dilate up to its up to 30% strain. And the same comparison plots for, in this case, undrained tests, where, again, they move to the same critical state, but what we're seeing in this case is a little bit less strength in our 1-to-1 versus our 2-to-1. And so we then wanted to explore the reasons for that difference. And in fact, we're currently doing some flat modeling, element scale modeling to see if we can numerically show why the difference is there. Some of the hypotheses are, you know, that the 1-to-1 strength may be the true value, likely is, and the 2-to-1 show reduced strength because of the tendency for that material to effectively collapse because of very non-uniform stress distributions. And so the implication there may be that we're underestimating the strength that we're using from these test programs when we use 2-to-1 samples. We don't want to completely ignore that perhaps there is some degree of interference with end caps that occurs at large strain. And so, again, that's something we need to be very careful about before jumping to conclusions, because that would have the implication of, you know, us overestimating strength if we use 1-to-1 samples. And again, more research needed to really understand if we can, you know, prove what that difference is. Some other implications, again, this is just another way of looking at the friction angles, and you can see the different slopes of these lines representing the MTC values, which is, of course, where that line intercepts the origin. We don't see any difference with the chi value, which is, again, the dilatancy parameter, but there is a noticeable difference in hardening, and again, the same reasons mentioned before, very likely attributed to the instability of those 2-to-1 samples relative to the 1-to-1. And so in conclusion, specimens of 1-to-1 deform uniformly, that's clear. The CSL log P space is virtually identical. There's a slight difference in friction angles that we're not quite sure the cause of, and more research needed there. And again, use of 2-to-1 specimens may be underestimating the strength. There are some other subtle differences with the north sand parameters that could affect modeling implications, and some of those in situ state interpretations. The CSL can be defined by 1-to-1, whether it's loose or dense, which is a huge improvement, especially when we're looking in that E log P space. And it is also advantageous at times we're limited with how much material we have to work with, and so being able to cut the volume in half essentially doubles the amount of tests that we can do. And so we're testing where consistency is desired. Especially with respect to critical state dilatancy, the use of 1-to-1 specimens is preferred. And with the caveat that we need to be a little bit careful with the strength. And so effectively what we're doing on our projects anyways is to be doing dense testing at 1-to-1 to get rid of this shear banding thing, which effectively limits the usefulness of those tests. But when it comes to interpretation of the frictional strength, we're tending to lean towards that lower bound given by both tests, just until we can conclusively show one way or the other why it's lower. Yeah, so that's it. That's the second one. And again, very happy to answer any questions that anyone might have.